So percent composition, empirical formulas, and molecular formulas. That's what we're faced with on this homework assignment. So here's the practice problem set that you guys are working on, and the first problem is, what is a compound's percent composition? So by that I mean, can you describe in everyday language what do we mean by percent composition? So for this, your book will be very helpful, and I just want you to read through the paragraphs that talk about percent composition and come up with a 1 or 2 sentence summary of what we mean by that. And I think by working through these problems, you probably have a good idea of what that is. So let me come over here to kind of a blank slate. And before I start working some of these problems on this worksheet for you, I wanted to start with a very simple example just to kind of walk through some of the mole ratios that you're going to be running into, which may be confusing or off-putting, because you're going to see some strange numbers, and I don't want you to be spooked by those. So if we work through this water example, I think that'll make it clear. So as you all know, the chemical formula of water, H2O, and let's say that we we came upon this liquid, and we didn't know for sure if it was water, so we submitted it to a lab, and they did an elemental analysis, and turned out that 11.1% of the sample by mass turned out to be hydrogen, and 88.9% by mass turned out to be oxygen. And that was really all they could do for you. They couldn't give you the chemical formula. This was as far as they could take it. But based on what you know now, you could take this result, these percentages by mass of the contributions coming from the two elements, and you could very reasonably arrive at that formula. So, how do we do that? Well, you simply you take each of those percentages, and we pretend that the total mass of the sample is 100 grams. Okay, and we've seen this trick before. Let me bring this down a little bit. And so if we have a 100 gram sample, then we pretend that the hydrogen is 11.1 grams, and to get the number of moles, because that's important in order to try to figure out the chemical formula. The subscripts are describing the mole ratios among the different elements. So you need to get everything into a mole basis. Okay, so obviously that's going to be 11.1 moles. Oxygen, 88.9 grams. Divided by 16.0, and let's punch that in the calculator real quick. 88.9 divided by 16 is 5.56. 5.56. Okay. Now we're in a position, now that we have both elements in terms of moles. We got moles of hydrogen, moles of oxygen. Now we're in a position to take a stab at the molecular formula. So we could say that we have hydrogen 11.1, oxygen 5.56. Now that's a very strange looking chemical formula, admittedly, because we're used to seeing only whole numbers as subscripts. But these numbers are based on an experimental analysis, and it's our job to take these numbers and try to get them to a whole number basis. So since we know that those subscripts are telling us the whole number ratios among the moles, then what we do is we just take the one that has the lowest number and we divide through by that number of moles. Okay, so we're going to divide both mole values by the smallest number of moles. Okay, and when you do this, okay, if we bring this down here, HO, obviously the subscript on oxygen is just 1. And then if you take 11.1 divide by 5.56, you should get, well, what you'll actually get on your calculator is 1.996. Okay, and you might say, you know, if you're a purist, you'll look at this and you'll be sort of in despair because you'll think, well, it's not H2O yet. It's H 1.996 to 1 mole of oxygen. What's going on? Well, remember that these problems that we're working, we're assuming that these percentage values are the result of experimental analysis. And as we all know, there is error. You know, human error, instrument error comes into play. And so these numbers are, you know, never completely accurate. They may not have the precision that we would like. So you're going to see numbers that are, you know, even when you divide through by the lowest number of moles, you're still sometimes not going to see numbers that are perfectly whole numbers. So you realize, though, that it's, you know, it's not a perfect world, and that's about as close to 2 as it gets. And so it is a-okay when a number is that close to a whole number to round it to the nearest whole number. And when you do that, then you do indeed get H2O. All right. So that's kind of a little preface to this whole problem set that I wanted to tell you about. Let's see. All right. Let me erase that. And there's one more thing I want to tell you about, which is there's going to be times when the mole ratio between two elements, let's say A over B, might be something like 1.5. All right. So, for example, you may have a case where you have, you know, A 1.48 and then B is 1. Okay, so this would be after you've divided through by the smallest number of moles, and so one of the elements is going to have a 1, and then the other element, or elements if there's 3 or more, you'll have some funny number like this. Well, again, if you know, because when you work on a lot of these problems, you start to see patterns, and so I'm just trying to you know, give you a little bit of the benefit of my experience. When you see numbers that are close to 1.5, then this is a perfect case where you want to multiply through by 2. Because if you multiply through by 2, then this becomes 2.96. Let me just confirm that on my calculator. Yep, 2.96. Oops. Sorry about that. I'm thinking one thing and writing another. 2.96. And then B is 2. All right. And again, we've got to cut those experimentalists a little bit of slack. That's about as close to 3 as it gets in the you know, in the experimental world. So that would be A3, B2. Okay, and it could have just as well gone the other way. We could have had something like this: A1, B 1.5. Same thing. Whenever you have 1.5, you know, think to yourself, what is the smallest whole number coefficient, such that if I multiply through by that coefficient, I turn everything into a whole number. All of my subscripts turn into whole numbers, and in this case, it would be 2. All right, so then you'd get A2, B3. Okay, so that's one scenario that you're going to see over the course of this. The other scenario is when you'll see a case where the ratios are mole ratio sluggish sometimes. A over B is something like 1.3 or 1.33. All right, so in this case, let's say you have a situation where you have A 1.35, let's say, and B 1. Okay, in this case, what is the smallest coefficient that you could multiply through by and turn everything into a whole number, every subscript? Well, here you could multiply everything through by 3, and if you do that, then you're going to get A 4.05, B 3. Okay, and again, that's pretty close to a whole number, so that would be written simply as A4, B 3. And as with this case, the 1.5 to 1 ratio scenario, here of course you can also have A1 be 1.35 or 1.31, and so you need to recognize, just heads up, if you see mole ratios that are around 1.33 or around 1.5, then don't despair. That just means you need to multiply through by a low number coefficient to convert the subscripts to whole numbers. Okay, and that's all that is. Okay, so with that, let's take a look at number 2. Okay, so this is problem number 2 from your worksheet. We'll probably get through this, and I'll probably need to stop and make this a 2-part video at least. So, but that's fine. All right, so number 2, we have arsenic 60.9% and sulfur 39.1%, and we've been asked to determine the empirical formula. Okay, so clearly we're going to need to make use of our percent composition skills. We need to do the old, hey, turn the percentages into 100 grams trick. So what that implies is we assume that we have 60.9 grams of arsenic, and when you look up the atomic mass of arsenic, you get 74.9 grams, which turns out to be 0.813 moles. Okay, so we've got 0.813 moles of arsenic. Sulfur, we assume that we have 39.1 grams of sulfur, and the atomic mass is 32.0 if we round, to the nearest decimal place. And when we do that, we get 1.22 moles. All right. So at this point, we say, okay, how can we put that data together? So we could come up with a chemical formula that looks like this: 0.813, sulfur 1.22. All right, but of course, that looks pretty ridiculous. So we've got to divide both sides by the lowest mole value, which is 0.813 for arsenic. And when we do that, what you find is, obviously that turns the subscript on arsenic to a 1. Sulfur then becomes, let's see here, where did that go? 1.50, I believe. 1.22 divided by 0.813. Yeah, 1.50. Okay, and based on our discussion before, you should realize that that is this case right here, and so we are not panicking. We're like, okay, no problem. All we got to do is multiply through by the number 2, and when we do that, the subscript on arsenic turns into a 2, the subscript on sulfur turns into a 3, and voila, that is our answer. Okay, excellent. Got to stop here. See you at the next one.